Welcome. We're going to do question 5 first, and then in a separate video, I'll do question 7 because it goes on to talk about back EMF, which I want to very briefly mention here. So question 5, reason why I want to do this is because it has a graph there that we want to work with. So hopefully you've read the question that we're about to do. It's a rectangular coil with dimensions 5 times 4, 12 windings, magnetic field 15 Tesla, and it goes through 1 revolution when a current of 0.5 amps flows in it. And we're going to calculate the initial torque on the coil. So this is a basic, very straightforward question. So the torque, question 5, let's get everything right way up. The torque would be NBIA sine theta. We are told that it's 12, B is 15, I is 0.5, the area is 0.04 times 0.05, and sine theta, if you look at the diagram, it is placed horizontally in the field, and we know that the alpha in this case would equal 0. That means theta is 90 degrees. Remember, alpha is the angle between the plane of the coil and the field, and from that we can get the theta, which is the angle between the normal and the field. And so in this case, it's sine 90 because it's maximum torque. Okay, and that's important in a few more moments. So calculating this, it's 12 times 15 times 0.5 times 0.04, 0.05, and we get 0.18 Newton meters. Okay. Now, let's have a look. I'll make sure that I've got the right answer before I go any further. Yes, I've got 0.18 Newton meters. Good. Now we have to draw a graph. Okay. It's not good enough just to simply go and whatever we do with a sine or a cos graph here. We actually have to scale this correctly. So putting this, I'll draw a set of axes over here to mimic the ones. Okay, we need to somehow scale 0.18. So I'm going to do 0.1 and 0.2. 0.1 and 0.2, nicely maybe a centimetre apart. You would have to decide that, and this would be torque in Newton meters. And 1.8 would be there. So it starts at maximum. Now on the horizontal, we have degrees going around from 90, 180, 270, and then the full revolution at 360. We know that at an angle of 0, theta equaling 0, okay, this is the angle as it turns through 1 revolution. Now, this is not theta equaling 0, this is alpha equaling 0, because at the moment we are horizontal. So we're at maximum torque. So these numbers here represent alpha, not theta, okay? So it's alpha equaling 0 at the moment. So we have a maximum torque at its position there. At 90 degrees, we are vertical. Going back, here's a diagram here. So initially we're there, and that's maximum torque. When the coil gets to the vertical position there, it becomes 0 torque. So at 90 degrees, we're at 0. At 180 degrees, the coil's turned back in this direction, but the torque is going to be in, it's going to be in an opposite direction, but we'll just continue it down through to down here. And then back to 0, and then back to where it came from. Now, we know this is not a straight line, going backwards and forwards there like that. We know that this has to be a function of the sine or the cos. And in this case, it is going to be a function of the cos graph because it's starting high and coming low. Okay. Now, can we have negative torque? you could have, if you thought that looks stupid, let's not have that, you could have quite happily have made an absolute value of it and got up there, because we haven't got, as you'll discover later on, any mention of commutators on this coil at all. So commutators are in our next lesson, which is all to do with the motor. So whether or not it has a split ring commutator would depend on whether it goes down here or up there. Okay, so that's question 5A and 5B, please. Thank you.